Hello and welcome to Mr. Linford's math course. Today we're going to be discussing the topic of addition and subtraction of radical expressions. We alluded in the previous episode dealing with simplifying radical expressions that there is a process in which you can go and combine them together. But that requires us to really have a solid definition of what we're going to call like radicals, similar to the idea of like terms when combining those together. And then we're actually going to get into how to go about performing the addition and subtraction of these radical expressions. Now, the first thing that we have to do is really define what does it mean to be a like radical, because these are the things that we're going to combine together. We need to think of this similar to the idea of like terms, right? If certain terms aren't the same thing, can you really add them together? For example, could you add x plus y? What is that combined? They don't combine anything. That's like adding apples and oranges, as the saying goes. But if I had x plus x, then I could say I have two x's. The similar idea works when it comes to radicals. We want to make sure that we're combining radicals that make logical sense. So, like radicals, we're going to define as being radicals or radical expressions that have the same, that's important, they have the same index and radicands. So, like radicals are radical expressions that have the same index and the same radicands. So remember, the radicand is the interior value underneath the radical sign. And index is what type of root are you taking? Is it square root, cube root, fourth root, whatever? So let's take a look at this example right here. We have 4 times the square root of 3 plus 6 times the square root of 3. Are these like radicals? Well, some things that we have to check are, we need to check the index. What is the index here? Now, these are both square roots, so the index, it's not written, but there's an imaginary 2 there. So yes, these are both of the same index. And then the radicand. The radicand needs to be the same. That's the value underneath the radical. And here, both of them are 3, so yes, the radicand is satisfied. So these are like radicals. That means we can go and combine them together. We can add these together. Now, we have to think, how do we go and add these together? We've never been told before how to add radical expressions. So we need to kind of come up with a way that makes sense to us. Well, one thing that we can do is think, well, 4 times the square root of 3, that means that we have 4 root 3's being added together. 4 times root 3 is root 3 plus root 3 plus root 3 plus root 3. And then if we have 6 root 3, that means I have 6 root 3's being added together. I'm running out of space. So there are 6 root 3's being added together and 4 root 3's being added together. And I'm saying to combine all of these together. Well, isn't this just one giant addition problem? How many root 3's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we essentially have 10 root 3's. So it seems pretty obvious how we're going to go and perform this addition. We essentially are just going to be adding the terms outside of the radical. Is it as easy as if we had 4x plus 6x equaling 10x? Yeah, it pretty much is. This is the exact same idea. The way in which we go about combining like terms, we're going to do the same thing with combining like radicals. The radical will stay the same, but the value on the outside will be the combination of the values on the outside. So we might want to make a little note to ourselves. I'll change colors here. But let's make a little note to ourselves that we are going to add the values outside the radical. So that's a big first part. We're going to add the values outside the radical. And we might want to also say to keep the radical the same. Meaning don't change it, right? This root 3 doesn't go away. Because if we had 4 root 3's and 6 root 3's, now we have 10 root 3's. Okay, we need to keep that constant. So very similar to working with square roots. Or, I'm sorry, for working with like terms. Now when we work with these square roots, let's see if we're comfortable combining these like radicals. We have 2 root 5's and we have 6 root 5's. So I know it's a little weird to think about, but imagine you had 2 root 5's and I gave you 6 more. How many root 5's would you have? Well, I would have 8 root 5's. Again, all that we're doing is we're combining these exterior numbers to get 8, okay? You can think of them kind of like the coefficients of these radicals. I guess I'll refer to them as that going forward, the coefficients of the radicals. So here we have 9 times the cube root of 2y minus 4 times the cube root of 2y. Well, 9 minus 4 is 5, and we leave the radical the same. Again, this is just like if I had 9x minus 4x. It's the same exact idea and technique. So here I have the cube root of 3, and I gave you another cube root of 3. How many do you have? Well, you should have 2 cube roots of 3. Let's try a couple more problems. We now are going to combine some positive and negative values. We have negative 2 times the cube root of AB plus 7 times the cube root of AB minus the cube root of AB. Again, all of these are like radicals. They all have the same index. They all have the same radicands, so we can go ahead and combine them. So let's add, or I should say let's combine, these kind of coefficient values on the outside. We have negative 2 plus 7, so that should be 5 cube root AB. And then we have minus the cube root of AB. So let's combine these now. So we did the first two. Now I have to combine 5 cube root AB with negative 1 cube root AB. So that should just become 4 and the cube root of AB. That's it. All we're doing is just combining the outside numbers and leaving the radicals the same. So let's go ahead and let's try number 5. 2, and then the radical has the TW, and we're subtracting the TW from here, so we should just have one of the TW radicals, right? Ooh, hopefully you're saying, no, that's not right at all. And why isn't it right? What's the issue here? Hopefully we have a big resounding, look at the index. There's an issue there. The indices are not the same. Try to trick you with this problem. So keep in mind that sometimes just because you're given radicals to combine doesn't mean they can always combine, right? You won't always be given like radicals. Now in this unit and in this section, you pretty much will. But generally speaking, there's nothing to say that two radicals have to be like and you have to be able to add them together. So in this case, if we wanted an answer to it, well, we would just have to rewrite what we're already given. Nothing combines. This is like trying to combine unlike terms, trying to combine X and Y, right? They're separate things. They don't really combine together. So be on the lookout for some of those. They'll be popping up later again. But let's get into some more complicated problems. Let's take a look at 3 times the square root of 8 plus the square root of 2. Now, initially, we look at this and we say, we can't add this together. Yeah, they're both square roots, so they have the same index. But these are different radicands, right? I got 8 on one, 2 on the other. So we would initially think, well, we can't simplify this. Can't be done. However, we should use our realization from our previous section of simplifying radicals to think, wait a minute, maybe we could break down the square root of 8 so that it has a square root of 2. Let's see if that's possible. It might be, it might not be. The only way you'll know is you have to test it. So we're going to break down the square root of 8. So let's do that to the side here. The square root of 8, we can break that into the square root of 4 times the square root of 2. Square root of 4 simplifies to 2 and root 2. Hey, so what do you know? This problem is really 3 times 2 root 2 plus root 2. So that's really just 6 root 2 plus 1 root 2. It turns out that these are in fact like radicals. We just had to simplify it down. So in this section, a lot of what you're going to be seeing are radicals that aren't simplified yet, where you have to break them down to show that they are like radicals and that they can then combine together. So our answer here is if you have 6 root 2's and I gave you one more, you now have 7 root 2's. So that's the idea with this section, or with this particular topic, being able to break it down. Now, could you do that from the beginning? No. Like, you couldn't just combine and say, I would have 4 root 2's. No. You have to simplify it and figure out, 1, are they like radicals after all? And 2, can they combine? Now, let's write a little process down for ourselves just to make sure we have this set. Step 1, simplify all radicals completely. Simplify them all completely. Break them down as much as you can. Once they're broken down, identify any like radicals. Identify any like radicals. So making sure that they have the same index and that they have the same radicand. Then, once you have those like radicals, combine the, I'll say the coefficients, combine the coefficients of those like radicals. Hopefully this process is a general one that we can use. We're going to come across more complicated problems, but if we stick with this process, we'll find a real kind of nice step-by-step way of tackling them. So let's take a look at the next one. Again, if we first look at these, we have 80 and 125 w squared as our radicands. Clearly, they do not look like at all. However, we should probably make sure, so let's go ahead and break them down. What I'm going to do is I'm going to break down each one individually in separate colors. I would recommend you pause the video, take some time to yourself to break each one down, and see if they are like radicals. I would recommend that you do this not as one giant problem where you just keep listing line after line after line and making it more and more complicated. Instead, I'd recommend that you simplify each of these individually. So grab some scrap paper, work individually, maybe color code some stuff, and then let's come back and see where we're at. So pause the video, take a couple minutes, and we'll see where we get when we come back. All right, well, hopefully you've had an opportunity to work through these problems. Here you can see my work at breaking down each of the radicals. I simplified them using the prime factor decomposition method. So I broke 80 down into 2 times 2 times 2 times 2 times 5, made my pairs of 2's here, and broke those down individually. So my final answer came to 4 root 5. I then broke down 125 into its prime factors, 5 times 5 times 5, and I figured out what the square root of w squared was separately. So I made my pair of 5's. Those just simplified down to 5. The square root of w squared was just w, and then a root 5 stayed by itself. So we ended up with 5w root 5. So hopefully you're able to come across these two radicals. It's good practice for us at simplifying radical expressions. Now, we're not done with our work. All we did was just simplify down these radicals. And we can see that, in fact, yes, they are like radicals. Because, let's see, the radical here is root 5, and the radical here is root 5. So we can go ahead and combine these together. So let's clear our workspace, and we're going to substitute these values back in. Okay, we had w times the square root of 80. Well, instead of 80, square root of 80, I'm going to write what it simplified to, the square root of 4 times root 5. And then we were subtracting 3 times, and instead of the square root of 125w squared, we're going to write what it simplified to, 5w times root 5. Okay, let's go ahead and let's keep simplifying this down. W times 4 root 5 is, we could just say 4w root 5, right? Again, the w doesn't go inside the radical, it still stays on the outside. Minus, let's see, 3 times 5 is 15w root 5. Okay, we're still just working with numbers on the outside of the radical here. So let's see if we can go ahead and combine these. One of the things you need to be on the lookout for is when you're going to combine radical expressions, yes, you need to have like radicals, but you also have to make sure, can these coefficients actually combine together? 4w and 15w. In this case, yes. But if one of these didn't have a w, then they actually couldn't combine, right? Because the coefficients need to be like terms as well. So just be on the lookout for some of that. But in our problem, we can go ahead and we can combine the 4w and the negative 15. So 4 minus the 15 should get us negative 11w. And the root 5 stays the same. So again, all we did was just combine the outside coefficients, got our value, and we're left with the root 5. So again, a little bit longer of a problem. A little bit more tedious, but not too bad. It's relying on all the same stuff that we know. We just have to simplify the radicals down, make sure that they're like radicals, and then go ahead and combine them together. Now, I would recommend when you do these problems in your homework and on the test, grab some scrap paper, get a different, colored pencils or pens and try to work with them separately. Try to break them down separately so you can make sure you're not doing too much at once and getting lost in maybe a sign somewhere or an exponent, okay? With that said, we're really going to need that for this problem. Here, we have 3 separate radicals. We have a 72b, an 8a squared b, and a 50a squared b cubed. This situation is really going to require us to be very careful and diligent in our work. This problem is not that complicated. We've done this before. We just did a problem like this. Except now, we have to be very careful in our work. We have to be very careful with our labeling and how we're going to go about working through this. What I recommend is pause the video, make yourself practice. Can you break these radicals down? Can you simplify them? It's great practice in testing your skills, okay? Try each one, see if you're able to do that, and when we come back, we'll check our work, okay? All right, pause the video, take a couple minutes, and when we get back, we'll see what our answers are. All right, well, hopefully you're able to go ahead and break down each of these radicals as follows. You'll see I color-coded each one. The first one broke down to 6 root 2b. The next one broke down to 2a root 2b. And then the last one broke down to 5ab root 2b. You can see my work here. I'm relying more on the method that deals with just kind of very carefully picking perfect square factors. You could have also have done the prime factor decomposition. That's fine too. I just didn't have too much room to work with here. So I worked with each one kind of more individually. Make sure that you're able to see how I broke down these b cubes over here. But with that said, we can easily go and see that, yeah, these are going to be like radicals. All of the radicals that we're left with are the square root of 2b. So we should theoretically be able to go and combine these. We just have to make sure that their coefficients match up. So let's go ahead and substitute back in what we have here. Let's see if I can fit that down a little below here. We have AB times, instead of the square root of 72b, we're going to sub in 6 root 2b. And then we're going to add 2/3 b times, instead of the square root of a squared b, we're actually going to sub in what that equals, 2a square root 2b. And then we're going to subtract 5/6 times, and again, instead of that square root of 50a squared b cubed, we're going to have 5ab cube root of 2b. Let me wrap that in parentheses really quick. All right, now that we have everything here, all we have to do is simplify each of these down. All we got to do is perform a little bit of multiplication. So we end up with 6ab times the square root of 2b plus, let's see, 2 times 2 is, so it's 4/3 ab root 2b minus, let's see, 5/6 times 5. Remember, these are like 5 over 1 and 2 over 1. So 5/6 times 5 over 1 is 25 over 6 ab root 2b. Hopefully you're seeing how we're going through and combining everything. Really, I'm just multiplying the numbers together, and then we just have an a and b variable left over in each of these. But you should notice that we have 6ab, 4/3 ab, and negative 25/6 ab. All of these are like terms, so we can actually go ahead and combine them together. So we can add 6ab with 4/3 ab minus 25/6 ab. We can go ahead and do that. I'm actually just going to use my calculator. A lot of people go ahead and actually they show their work at how they're combining the like terms and how they're making common denominators. That's fine, but notice how long this problem is. It's a very lengthy problem to deal with. I would be a little more comfortable just working with my calculator or working with some type of technology to actually do the computations for me so I can get to more complex problems. If you use your calculator and you combine the 6, the 4/3, and the negative 25/6 together, you should end up with 19/6 ab. And then the radical stays the same, the square root of 2b. That's going to be our final answer. Maybe your answer is a mixed number instead of 19/6. Maybe you have an unsimplified version of that. But as long as it's equivalent to 19/6, you're good. So, all of this said, we can see this really isn't that complicated of a problem in the sense that, I mean, we know the steps to do. It's just a bit tedious. And really, what it relies on is your organizational skills, making sure that you're able, one, to simplify things down, but really that you're able to simplify down in a very organized way. So again, I recommend getting scrap paper, using different colored pens or pencils, and trying to really organize how you break everything down. And notice that we were checking our work along the way. We made sure that we had the like radicals. We made sure that we had the like terms that we're going to add together. So that's a big concept for us. So making sure that you're checking your work along the way so that you can finally combine your answer to one thing at the end. Now, let's go ahead and let's try a couple true or false problems before we wrap up. The first problem says the square root of x plus the square root of x is equal to the square root of 2x. The second problem says 6 times the square root of x plus 5 times the cube root of x is equal to 11 square root x. And then the last one says that the square root of c squared plus d squared is equal to c plus d. All right, if you're feeling brave, pause the video, come up with your answers of what's true and false, and maybe put it in a comment down below if you're feeling brave. But let's go ahead and work through some of these and test to see our thinking. The first one, the square root of x plus the square root of x is equal to the square root of 2x. Hopefully, you're saying very loudly, that is false. Because what is the square root of x plus the square root of x? That's 2 root x's, okay? Remember, we're combining the coefficients on the outside, and there's kind of imaginary 1 coefficients on the outside here. So that doesn't mean we have 2 on the inside. That doesn't affect our radicand. It just affects the outside. If you have a root x and I gave you a root x, how many do you have left? Or how many do you have now? You have 2 root x's. All right, the next one, 6 times the square root of x plus 5 times the square root of x. We see that they're the same radicand, but hopefully you noticed different indices. One's a square root, one's a cube root. So can these combine? No, they can't. Hopefully we heard a big false in our statement there. We cannot combine these together. They're totally different, not like radicals. Now, number 3 is more of a tricky problem that students tend to come across. The square root of c squared plus d squared, is that equal to c plus d? Well, we're thinking that if we can take the square root of c squared, we get c, and the square root of d, we get d squared. Or, I'm sorry, the square root of d squared, we get d. So maybe that should work. Now, keep in mind that when we split up radicals, we have to split it up in terms of multiplication. C and D would have to be multiplied together, not added. So in this case, we can't use that property that says we can go ahead and split them up. So we have to think a different way. Well, if you're kind of stuck about, does this work, does it not, it's sometimes helpful to plug numbers in for C and D. Just plug some numbers in and see if they work. Let's see. I'm going to pick something other than like 0 or 1. Pick something interesting like, let's C be 2 and D be 4, for example. Okay. The square root of 2 squared plus 4 squared, is that equal to 2 plus 4? All I did was pick some numbers for C and D and sub them in. If this is truly equivalent, if it's truly equivalent, it will work for any number you pick. So let's see, that's the square root of 4 plus 16. That should equal 6. Well, the square root of 4 plus 16 is 20. That doesn't equal 6. So, turns out no, this is also a false statement. So all 3 of these were false. None of them actually worked. These are 3 very common misconceptions, work I see a lot of students do from time to time. This first one is a big one, where they combine the coefficients but they put it inside the radicand. Be careful with that. The radical needs to stay the same. And then trying to do properties like this. Be very cautious of coming up with your own techniques for things, right? Coming up with your own theorems or formulas for things, because unless they're really tested, you don't know necessarily if they're true or not. So just be cautious with that. If you have any questions about any of the problems that we've done in this video, or any of these true or false problems, or if you have any comments about the video, feel free to let me know. My email is klinford@wccnet.edu. That's KLINFORD@wccnet.edu. Feel free to let me know what you think, or drop a comment down below, and let me know if you have any questions. Otherwise, take care.